Discovering planets around other stars is one of the most fascinating and complex challenges in modern astrophysics. This field of research represents one of the most advanced frontiers in the study of the universe, requiring the use of extremely sophisticated technologies and high-level data analysis techniques. When we look at the sky, stars appear to us as simple, infinitesimal points of light. The planets orbiting around them are even smaller and harder to detect, often hidden by the blinding light of their parent star. In most cases, it is almost impossible to observe these planets directly. But how then do we discover these distant worlds, known as exoplanets? There are several methods for detecting the presence of extrasolar planets, but one of the most effective and productive is undoubtedly the transit method. And that is exactly what we will talk about today, starting our journey with a brief historical introduction. From Giordano Bruno to Kepler, a long-standing intuition. There is not just one world, one Earth, one sun, but as many worlds as there are luminous lamps around us. These are the words of Giordano Bruno, who in the 16th century hypothesized the existence of infinite worlds orbiting around other stars. A radical vision for the time which cost him his life. Bruno was condemned to the stake in 1600 in Campo de' Fiori, Rome. Yet today that intuition has become science. More than 4 centuries later, we not only have the certainty that planets exist around other stars, but we are also able to detect them, study them, and in some cases even examine their atmosphere. The Kepler mission and the exoplanet revolution. The true turning point in exoplanet discovery came in 2009, with the launch of the Kepler space mission, dedicated specifically to the search for extrasolar planets. Kepler was designed to observe a fixed portion of the sky, focusing on thousands of stars in the constellations of Cygnus and Lyra. The telescope constantly monitored the brightness of these stars, looking for small variations that might indicate the transit of a planet in front of its star. In 2011, just 2 years after the launch, the Kepler team released its first results. Over 1,300 planets discovered, about 2,000 of which were similar to Neptune, and 207 Earth-sized planets. However, the mission faced an unexpected setback in 2013 when 2 of the reaction wheels necessary to maintain the telescope's pointing broke. It seemed like the end of the mission, but engineers found a brilliant solution, using solar radiation pressure to stabilize the telescope. Thus, the K2 mission was born, which continued the search for exoplanets with a slightly different strategy, observing different portions of the sky in successive periods. Kepler and K2 revolutionized our understanding of exoplanets, discovering thousands of them. Currently, we know of over 5,690 confirmed exoplanets, more than 4,200 of which were discovered thanks to these 2 missions. The transit method, how it works. The transit method, which has proven to be the most productive in the search for extrasolar planets, is based on a simple but elegant principle: the reduction in a star's brightness caused by a planet passing in front of it, much like a solar eclipse. When a planet transits in front of its star, it blocks a small fraction of the starlight, creating an observable dip in brightness. By measuring these small variations over time, we can deduce the existence of a planet. Imagine looking at a graph representing the brightness of a star over time. During a transit, you would see a consistent decrease in brightness, followed by a return to the original level. This method not only allows us to detect the presence of a planet, but also provides important information about it. How long it takes to orbit its star, its size, estimated based on the amount of light it blocks, and, if we're lucky, even the composition of its atmosphere. Planetary atmospheres and spectroscopy. One of the most extraordinary advantages of the transit method is that, in some cases, we can also study an exoplanet's atmosphere. When the star's light passes through the planet's atmosphere during a transit, some chemical elements in the atmosphere absorb specific wavelengths of light. This creates spectral signatures that can be analyzed, allowing us to understand which gases make up the planet's atmosphere. In this way, we can discover whether a planet has an atmosphere rich in oxygen, methane, or other compounds that might potentially indicate conditions favorable to life. The limitations of the transit method. Despite its successes, the transit method also has some limitations. First of all, it only works if the planet's orbit is aligned in such a way that it transits in front of its star from our line of sight. This means that many planets cannot be detected using this technique. Moreover, the method does not allow us to measure the planet's mass, To do this, we must combine the transit method with other techniques, such as Doppler spectroscopy, which allows us to measure the gravitational pull the planet exerts on its star. Another limitation concerns planets far from their star, like Uranus in our solar system, which takes 84 years to complete an orbit. To detect a similar planet using the transit method, we would have to observe the star for decades, which is often impractical. This explains why most of the planets discovered so far are large and close to their star, like the so-called hot Jupiters, planets similar to Jupiter but in very close orbits. Future challenges and combining methods. The transit method, despite its limitations, has transformed our understanding of the cosmos. But to further improve our ability to discover exoplanets, it is essential to combine multiple observation techniques. Using increasingly sensitive instruments, such as the James Webb Space Telescope, along with future missions like Plato and TESS, will allow us to push the boundaries of exoplanet research even further. Thank you for watching. If you enjoyed the video, please give it a like to support us.